In this video, we're going to look at the different ways in which quadratics can be displayed and graphed. And one of the things that's important to understand is that quadratics can be given in vertex form, which we covered in a previous unit on transformations, in which the equation is described with an A and a B, an H and a K, find the vertex and finding the vertical and horizontal stretches. But it can also be expressed in standard form, which is a little bit more standard in the quadratic chapter. The main difference is this one, the vertex form, is much more easy to graph directly, where the standard form, it has to be manipulated a little bit more to be able to get items to work out. So my advice when you're reading these notes, you're listening to these notes, is I would read along and I would stop every time you see a bar. I would stop the video and write down the information. So vertex form, as you've already seen, it's the one with the A, the B, the H, and the K. Note that H is always opposite of what it appears. So if there is a 3 here in the vertex, it looks like it's -3, but this would actually be 3. And if K were 4, it would be exactly what you think it would be. It would be 3, 4. Just don't forget that H is always opposite of what it appears. It's defined as negative. So just keep that in mind. And negative means opposite in math. For the standard form, there's a little equation to learn, which is, please note also that A and B in this standard form, they are not the same A and B as over here, right? The A and B in here is alphabetical orders representing coefficients, where over here they represent a vertical and horizontal stretch and compression factor. So what we're going to do is we're going to take, to find the vertex, we would do minus b divided by 2a. It's like the quadratic formula without the plus or minus, all that stuff in it. It's the same formula actually, minus that part. And then this part means I'm going to take the answer and plug it back in. So let's say I found the answer to be 2. What I would do to find f of minus b over 2a is I would take the 2 and I would plug it back into these x's, and then I would use Gelmdorf and simplification to figure out what it simplifies to. And we'll see an example of that just in a couple of minutes. All right, so I would pause and I would then write that down. So within quadratics, there's also symmetry, and this is a very important thing. There are applications for the axis of symmetry. And the axis of symmetry is simply the vertical line that goes down the middle of a parabola, which is the name of this shaped graph. So it's a graph of a quadratic. The shape is called a parabola. And the axis of symmetry is the line, the vertical line that goes through the vertex and produces symmetry on the left and the right side. And so in vertex form, it would just be the equation x equals h. Please remember the mnemonic device Hoy-Bucks, which stands for horizontal lines have 0 slope and have an equation of y. And the Bucks part is vertical lines, which is what we're using in this part, have an undefined slope, and their equation to describe them is always an x. The x matters when you're describing these. So the symmetry line for vertex form is x equals h, and the line equation in standard form is x equals the same location. These are the same thing. They're the exact same thing. It's just different to find them based on the equation. So it'd be x equals minus b over 2a. All right, so pause and write down notes. All right, so the x-intercept is a concept we've seen before, and the x-intercept graphically is the point where the curve crosses the x-axis. It is labeled x, 0. Please keep in mind, I didn't quite make it in there, so I'll draw it, that this is the same concept as the discriminant, right? The discriminant from the previous lesson will tell us the number of x-intercepts. If it has 2, none, because it's they're complex, or if there's 1, because the vertex is on the x-axis. Algebraically, the way you find this is you let y equals 0 and solve for the x values. And this is why we learn how to solve before we learn how to graph. Because if you look at what happens here, I took the vertex form, which we learned right up here, and I set it equal to 0. And then I'm going to have to solve that for x. And in the standard form, this should look very familiar. I mean, you saw problems in the last assignment, that maybe look like this. And what you were doing when you solved this equation was you were solving for the x-intercepts. Over here, you have not seen problems that look like this too often, but let's see if we can figure out what method it is. We actually have seen problems like this, but we just haven't seen them this complicated with all these different letters. So this, believe it or not, would be the square root method. We would subtract 3, divide by 3, then we would take the square root, divide by 2, and add 1. So those are methods we've seen. So to solve for x, you find the x-intercepts using the square root method, as I just mentioned. For here, to solve for x, you find the x-intercepts using the zero product property by factoring or completing the square or the quadratic formula. So this part, you can really see why we had to learn how to solve before we learned how to graph. So I would pause and write down any pertinent notes that you need there. So the y-intercept is the last concept we need to learn for graphing, and y-intercepts are a universal term as well. You can't find y-intercepts by solving. You actually have to plug 0 in. So it's actually much easier. To find the y-intercept graphically, it's the point where it crosses the y-axis. So if I was looking at a graph, the graph would cross the y-axis somewhere. There would only be one ever. There always is one. Unlike the x-intercepts, there could be none. The y-intercept, there is only one. There's not going to be two, just one. You simply plug 0 in, and it's going to be labeled 0, comma, whatever that answer is, y. Algebraically, you let x equal 0, meaning you plug 0 into the function, and then you simplify that using the order of operations Gelmdorf's. So what we would do is we would just plug 0 in for x. So if I had f of 0, and these numbers were filled in, here I would have, a 3, a 2, and then the x right here would be minus 1 squared plus 3. I just made that example up. What we're going to do is we're going to put a 0 here and simplify. So you would have negative 1 squared, negative 1 times 2, then squared, then times 3, then plus 3. Over here, it's a much easier process, and I'll show you why. In standard form, it sure is easier, because if I had an example like this, where x was 0, it always comes out to just be whatever c is. And that makes the problem a whole lot easier to deal with. In standard form, the y-intercept will always be whatever c is, because these two things, when you plug it in, they just cancel out. That's the zero product property, really. You multiply anything times 0 with 0. So for the vertex form, to review, you're going to reduce using the order of operations to find the y-intercept once you plug 0 in. Same thing for the standard form, but you always will get c, which that'll make it so much easier on a test. If you realize in standard form, if someone asks you what the y-intercept is, you can literally just circle c. Just make sure you write it correctly. Like in this example, the y-intercept would actually be 0, 5. Okay, so I hope that makes sense. You might want to go back and look at some of it again and make sure you took good notes. So the first thing we're going to focus on in our examples is just to review how transformational graphing works with quadratics. I did mix it up a little bit here, and I'm asking you to graph f of x minus 1 minus 4. And I did this just so you can see a different way of how it might be presented to you on an SAT or in a different teacher's class. So the direction says f of x is x squared. Write the quadratic equation and graph it by using transformations. So what that means is that f means x squared. So the first thing I want you to do is to write down, well, what is the equation? So the equation f of x in this example is x minus 1 squared minus 4 from the previous chapter. And now I want you to go through and remember how to find the vertex. So remember, it's going to be the opposite of h once you factor everything out. There isn't anything to factor out, so it would just be 1, not negative 1, opposite of h. And then minus 4. The axis symmetry, which is new to this chapter, is x equals 1. You must have the x equals for it to get full credit on an assessment. And the reason is if you just write down 1, does that mean x-intercept, y-intercept, vertex? What is that? So you have to label it, that way I know what it is. We're going to find the y-intercept first because it is easier than the x-intercept and it's new, because remember, x-intercepts are simply the same thing we did when we solved. So y-intercept is f of 0. In fact, there are SATs and questions later in calculus where they just refer to the y-intercept as f of 0. So they are one and the same thing. So we're going to simplify this expression. So 0 minus 1 is negative 1, right? And you square that. And then you subtract 4. Please remember that anytime you square something, it is positive. So this will be 1 minus 4. So this comes out to -3. So the y-intercept, you want to label it correctly too. Don't say it's -3. It is 0, inputted 0, outputted -3. It's very important in this chapter, since we've already learned how to do this before. The importance now is, did you write things correctly in their correct format? To find the x-intercept, you set the equation equal to 0. And this is universal. This is not just for quadratics or for just this chapter. In fact, absolute values, when you set them equal to 0, you're finding their x-intercepts. Later on, when we learn about other things, that's the same process. We're now going to reverse this using, solve this using reverse order of operations or Gelmdas. So we're going to add 4 since it's at the bottom of Gelmdas. All right, zero that out. Sorry, that doesn't zero out, my apologies. This does. So this is 0 plus 4 is 4. You can see how easy it is to make just a small boo-boo. Your brain just plays a trick on you. Please make sure that you're being careful. All right, so here we're going to take the square root. Make sure that when you take the square root in solving, you include a plus or minus. So this comes out to plus or minus 2. And this comes out to x minus 1. This means that I'm going to have two equations. So you might remember this all the way back to absolute value. You're going to have x minus 1 is equal to 2. And you're going to have x minus 1 is equal to -2. Here you're going to add 1 to both sides. And you get 3. Here you're going to add 1 to both sides. And you're going to get -1. Keep in mind, on an assessment, these would be marked off by a point. They are x-intercepts now. So this is 3, 0, and this is -1, 0. That's very important moving from this point on in Algebra 2 to write things in the correct format. So let's put all this together. Let's take a look at the graph. So when we take a look at the graph, I went ahead and graphed the axis of symmetry using a line. And so that line is x equals 1. And now we're going to graph the vertex at 1, -4. My x-intercepts are right here at 3, 0, and -1, 0. Okay, notice that symmetry, that they're the same distance, 1, 2, 3, right? The same distance away on each side. Actually, I graphed that one incorrectly. It's at 4, so 1, 2, 3 is there, -1, 0 is there. And that's why that axis symmetry is so important, and it helps check your work, as you can just see that happen. And then here, the y-intercept is 0, -3, which would be here. Now, why did we do it this way? The interesting thing is, if we did this problem from the previous chapter, it would come out to the exact same answer. So I'll graph it again using a different color, and you can see what I mean. So if I did this with the previous chapter, I would have started at 1, -4 as my vertex, and I would have gone over 1, square 1 is 1, -1, square 1 is 1, over 2, square 2 is 4 up, left 2, -2, square 2, -2 is 4. Notice they're all the same points. And so this is really supposed to just help you make those correlations as you're learning it. All right, so let's take a look now at the next problem. Very similar, but there will be a stretch, which we'll look at that as well from our previous chapter. So again, a little disorienting at first because it asks you to do f of x minus 8. Now, what is that? Where is that? Remember, f of x is x squared, so the first thing you do is write down the equation. So the equation for this one is f of x is equal to 2x squared minus 8. Please keep in mind that this parentheses is closed, so there is no h, there's only a k. So the vertex will be 0, and I always tell my students, no parentheses, no h. It's really important to remember that. There's no parentheses, so that means that 8 has to be a k. That means our axis of symmetry is going to be x equals 0. Make sure you have the x equals. And to find the y-intercept, we're going to find f of 0 by plugging 0 in. And this is an interesting problem because when I plug 0 in, when there is no h, I actually have it in standard form, which is really interesting, that when h is missing, standard and vertex form are exactly the same. Because this will cancel. 0 squared times 2 is 0, and then minus 8. So f of 0 is -8. Please keep in mind if you ever see this on an assessment, especially in SAT, this means y-intercept. But we're going to write it like this. I plugged in 0 and I outputted -8. I want it in the point format in this course. So the x-intercept is to set the problem equal to 0 as opposed to plugging it in. I'm going to use, well, what method makes sense? There's no bx term, so I'm going to use the square root method for this problem. We're going to add 8 on both sides. Just remember that everything you've learned in this chapter, it's all consistent. There's nothing really new. It's just how do I use the information I learned. This zeroes out or cancels out. Here I'm going to, I did the bottom part of reverse Gelmdas, so I'm now going to divide by 2, giving me 4. And this, of course, will inverse. Here I'm going to take the square root, and when you take the square root, you need to put a plus or minus on it. So we have plus or minus 2 is equal to x, and I did this on purpose so you could see the difference. Here we had an equation to solve, but here there's nothing on the inside, so my x-intercepts are in fact just going to be -2, 0, and 2, 0. It is important to not leave it like this. This is not the answer when I graph. This is. All right, let's take a look at the graph. In this case, we have an 8, so we're going to need to go by 2's. I put the axis symmetry here at x equals 0. It is, in fact, the y-axis, which is a little bit interesting that the when you have x equals 0, that's going to be the y-axis. So now what we're going to do is we're going to graph the other pieces of this. The vertex is at 0, -8. So 0, -8, and that is in fact the y-intercept, because when we found that, yep, the vertex and the y-intercept are the same, and you can see that immediately when you graph it. And then we have our x-intercepts at -2, 0, and 2, 0. And that would be it. I need to go back and graph this one. Don't ever leave the dots like that. You're always going to want to go ahead and graph it. And then here we can graph this one, and then we'll take a look at what it looks like, right? So from the previous chapter. So if I looked at it from the previous chapter, our vertex would obviously be at 0, -8. That part didn't change. The question is, how do I get to this dot? Well, we had a vertical stretch of 2, and we're going by 2's. So over here, we would go 1, which is half a box, and then up 1 multiplied by 2. It's right there. Here we'd have -1 multiplied by 2. It'd be there. Oops, a little bit off. And then here's the dot that actually makes our x-intercept, so let's pay close attention to this one. I would go over 2, I would square that and get 4, but we had a 2 as a lead coefficient, so we have 2 from our squaring, and that becomes squared, so we have 4, and then we multiply times 2, so we end up going up 8. So over 2, square is 4, multiply times 2, 8 above the vertex. Same thing here, -2 squared is 4, and then multiplied by the stretch goes there. So it all works out perfectly from the previous chapter. So in these examples, we're going to explore how to use x-intercepts to put an equation into standard form. We've already learned how to solve. Solving from the previous assignment is the same thing as finding an x-intercept. So now the question is, how do I take the answers and regenerate the actual function? So in the first example, we're going to write an equation having given the x-intercepts or solutions. And keep in mind that this format means it's a set of answers. So keep in mind that this really means that this is x equals -5. And this answer over here is really x equals 4. And what we're going to do to make the function is we're actually going to move this back over here, right? So if we move this 5 back over to this side, it will now equal 0. Which what we're trying to gain here is we're trying to gain what we had before we used the zero product property to get the answer. So here we have x plus 5 equals 0. Here when we subtract 4, we'll get the other factor. So here we have x minus 4 equals 0. And then those two will produce the factors. So the function f of x that produced the answers -5 and 4 was produced with the factors x plus 5 and x minus 4. And then to put it, because the directions want you to write this in a standard form, we would then use the box method to reassemble this. So x plus 5 here, and x minus 4 here. So we would have x squared. X times 5 is 5x. X times negative 4 is negative 4x. And negative 4 times 5 is negative 20. Like terms are here. So we get f of x is equal to x squared plus x minus 20. And if you were to graph that on Desmos or a calculator, you would see it across the x-axis at these locations. Now that being said, you could even do it when you get answers like this that would have come from either the quadratic formula or completing the square. So keep in mind that this answer means that we had one answer as x equals 1 plus I root 2. And this answer here, I'll just change color so we can keep them straight, would be x is equal to 1 minus I root 2. So we're going to follow the same process we did here. We're going to move things back over to figure out what it would be like if we could use the zero product property. Keep in mind we did not in this case because we would have had to have used the quadratic formula. Let me put this one on this side too, negative I root 2. All right, so these canceled, giving me 0. And over here we have a big list of stuff, x minus 1 minus I root 2. It doesn't really matter the order you put these in as long as you maintain that order on the other answer. Same thing, we're going to subtract 1 on both sides, and we're going to add this time. Keep in mind we add that. And you might be really keen and realize that one of them is added, the I, and one of them has subtracted the I. And what that means is, like in here, here we have x minus 1 plus I root 2. And you might remember from earlier in this chapter that those are actually conjugates. See that and that? They're conjugates, which is going to be really important when you see what happens next. So we are now going to do the same thing we did here using the box method. I'm going to put this one going down the column here. And I'll put this one going across. All right, again, it doesn't matter the order as long as the order is the same for both of the answers. So here we have x squared. Here we have negative x. Here we have negative x I root 2. Looks crazy, but it's going to cancel because remember we mentioned the conjugate occurring here and here. Here we have negative x. Here we have positive 1. Here we have positive I square root of 2. Here we have positive, be careful. So here you have positive xi root 2. You would put a little plus sign there if you want to. This one would be negative I root 2. And down here we have negative I times I, which is negative I squared. Yes, we're going to change that in just a minute. And then root 2 times root 2. Remember, you would combine the bases there to get root 4. So let's work through this box method. Again, the box method is such a nice way to handle things. Again, notice here we have like terms, right? So like terms appear on the diagonals. Now watch this. There are like terms in this diagonal and they cancel. Negative xi is going to cancel with positive xi root 2. Same thing here. These are like terms, so they cancel. That's what the conjugate does. The conjugate takes every imaginary number in the problem and cancels it. And you might say, well, what about here? Well, this will be canceled because we have negative I squared. Remember, I squared is negative 1, and then the square root of 4 is 2. So if I put all of this together, this comes out to positive 2. You can put a little plus sign if you want to there. And that will combine with this 1. So the equation, the f of x, the function in standard form that produced these answers using either the quadratic formula or completing the square, would have been x squared. These two make negative 2x, and this one make plus 3. And you just think about that carefully. There's no way to take factors of 3, 1 times 3, and keep in mind this is asking you to add to get 2. It would work if that were a minus, but there's no way to add these factors to get 2. So this is clearly unfactorable. And if you were to work it back through with a being 1, b being negative 2, and c being 3, you would use the quadratic formula or complete the square to get these two answers. All right, so now we're going to put it all together and do some examples of graphing from the beginning of the note. So if you need to, you might want to go back and review the different types of things we're going to do in the graphing section. And then I'm going to do all of them at this example. So the first thing it's asked you to do is find the discriminant. And the reason you want to find the discriminant is because it's going to tell you what kind of X-intercepts you'll have, which is very useful before you move forward. So part A, we just want to find b squared minus 4ac. And once we do that, that's going to be done by a is equal to the coefficient here, which is a is equal to 1. B is going to be equal to 6, and C will be equal to 5. All right, so once we do that, we're just going to plug them into here. So A is, so this will be 6B minus 4 times 1 times 5. And I try to make these numbers so you don't need a calculator. It is good to practice them without it. This could potentially be on an SAT without the calculator at hand. So this will just be 36. There's only one minus in this list, so this will be negative, and then 20. So this comes out to 16. So this tells us 3 things. It tells us we have 2 real answers. Okay, it's really important to understand that. 2 real solutions. It also tells us that we have 2 X-intercepts. And very helpful for actually finding those X-intercepts, it actually tells us the problem is factorable. Remember, if this number, the discriminant, comes out to a perfect square, where 16 is a perfect square, then that number, being a perfect square, will tell me that it will factor when I ask for the X-intercept. So part 1 is done. Let's talk about putting this in vertex form. So to put this in vertex form, remember, we're going to complete the square. To do that, let's take a look at how to do that. So putting this in vertex form is done by doing the following. We are going to move the 5 over to the other side because we want to create a blank there so that we have room to complete the square. So now we have f of x minus 5 is equal to x squared plus 6 plus a blank. That blank is going to be filled in by completing the square. Remember, completing the square is simply to take half of b, so 6 divided by 2, and square that number. So that will be 3 squared, which is equal to 9. So put a 9 there. Don't forget to add it over here. You are balancing an equation. Then you will balance this side, so f of x plus 4. That is the h that you've seen many times. Well, almost. We'll have to move it around. This will then factor. So maybe at this point, if you wanted to factor it above here and say, okay, this is going to be x plus 3, remember that this number is always the same thing that you have right here. And so why don't we just go ahead and write x plus 3 squared here, because there are 2 of them. And to put it in our format for algebra 2, we like to move the h back over. Again, if you're in pre-calc and you see that, you'll realize that sometimes pre-calc will actually leave it over there when you get to a certain section called conics. Depends on your teacher and what they prefer. But this year, we're going to move that h back over, and there we have our vertex form. So what is the vertex? Remember, the vertex is going to be the opposite of this number right here. So that would be negative 3. And then comma k, which is negative 4. And the new terminology for this chapter is the axis of symmetry. And the axis of symmetry is going to simply be x is equal to the first number. So x is equal to negative 3. Those are going to be important on the graph. So now we're going to find the x and y intercepts. And as you can see, this is just a great review of all the concepts so far from this chapter. So the x-intercepts, we know it's factorable. We're going to find the x-intercepts by setting it equal to 0. We know it factors, so this told us that. So we'll be able to do factorization pretty quickly. It is going to be 0 is equal to the original problem. This factors pretty readily because, again, we're doing an addition problem, and we have the choice of 1 times 5. Or that's it, right? And 1 plus 5 is 6. So we're going to do, okay, what's going to be x plus, remember, it's going to be positives, 2 positives. When this is an addition sign, these have to match, and they always are equivalent to the middle term. It's just going to be 1 and 5, because 1 and 5 multiply to 5, and they add the 6. And then you're going to use a zero product property. x plus 1 is equal to 0. So x will equal -1. And then here we have x plus 5 is equal to 0. So x will equal -5. Please keep in mind that these are x-intercepts, so we're going to want to write them like this: -1, 0, and -5, 0. To do the y-intercept is similar, but actually always easier. And if you go back and look at the notes in standard form, it's always just c. So you could already know that it's 0, 5, but let's see why that happens. So if I do f of 0, and I plug the 0 into all the x's, I'll have 0 squared plus 6 times 0, and then plus 5. These will cancel out, so I get that f of 0, which is the code in math for y-intercept, is equal to 5, but I'm going to want to write that as 0, inputted 0, outputted 5. And then the next thing you're going to do is just put all this together on paper. Let's see what it looks like. We'll start with the vertex. So if I put the vertex on a graph, that's going to go to my graph paper. We're going to go by ones. So -3, -4, which would be right here. Notice I went ahead and put the axis of symmetry there. My y-intercepts are -1, right? -1, 0, so here. And -5, 1, 2, 3, 4, 5, 0. Notice the perfect symmetry. My y-intercept is 0, 5, which is here. This tells me that I have two x-intercepts, which you can clearly see. So when I graph my graph, I can graph it pretty easily. And you can even, if you go back to your vertex form, practice your skills from Unit 2. Start at the vertex. There is no lead coefficient. So we would go 1, 1, as you can see there, 1, 1, as you can see there. 2 square is 4, -2 square is 4. All right, let's take a look at another example. Okay, so in this example, what we're going to do is we're going to take a look at what happens when some pieces are missing. It actually makes the problem easier if you know how to identify it. So this goes back to the solving. When we did solving, there's no c value. What that means is that c is actually equal to 0. But what it means for factoring is it means I'm going to factor using the Gcf method. So let's see what the discriminant tells us about that, right? Discriminant should tell us that it factors. And let's see if that holds true, right? So A is 3, B is 9, and C is 0. So B would be 9 squared, and then -4 times 3 times 0. This entire thing will cancel, giving us 81. So that's why it will always factor if there's no C, because it will always just be a number squared. So that tells us again that we have two real answers. It also tells us that we have two x-intercepts, and it tells us that it is factorable. All right, so knowing that, let's move through the rest of it. How do we put it in vertex form? Well, vertex form is to take the problem and move over the C. Well, in this case, the C is already missing, so we can just go ahead and put a blank right here. Boom. We don't have anything, don't need to move anything over. Don't forget that our next step will always be to factor out a lead coefficient. So I'm going to factor out 3. I did not do that on the previous example because the coefficient was 1, which made it unnecessary. And since this problem was a little easier with the blank there, I made that just a little bit more fraction-y. So we're going to take b over 2 and square it to complete the square, which will be 9/4. So we're going to put a 9/4 in the blank here. Please remember that when you add that over here, you're going to have 9/4, but then times this, because this would distribute. So we're going to multiply that times 3. And I know that that's kind of weird, but that's okay. I did that so that you would not have to add it to anything, just for practice with that. So that would be 27. Remember, there's a 1 on the bottom. So that would be 27/4. And then over here, we have the factorization, which the factorization is always just this number. So it's going to be x plus 3/2 squared, because the way we got this is x plus 3/2, and then another x plus 3/2. Just keep in mind that if you ever get stuck with completing the square, just remember that the answer is actually already on your paper right here. All right, so then we just move that over. So f of x is equal to 3x plus 3/2 squared. And then to move this over, we're going to subtract 27/4 over to the other side. Okay, and so that will give us our vertex. And yeah, it's a weird vertex, but of course you can always use a calculator and estimate that as a decimal. That's actually not a bad decimal to use, so just keep that in mind. All right, so the vertex would be negative 3/2, always opposite of h, and then comma 27/4. The axis of symmetry, which I'll just abbreviate axis of symmetry, is always the number that's the first part of the vertex, but you got to remember to put an x on there. So x equals negative 3/2. If you don't do that, you won't actually graph a line. So you want to make sure you have a line. All right, let's talk about the x-intercepts. This will be a really easy part as long as you remember that if their c is 0, then we are going to be doing Gcf factoring, which is the first kind of factoring you learn, but kids forget all the time. So to find the x-intercept, we're going to set the problem equal to 0 and use Gcf factoring. And when you do Gcf factoring, one of your answers will always be 0, 0, which is really important for the next step as well. So we're going to take out the common 3 and the common x by dividing. So 3x squared divided by 3x is x, and 9x divided by 3x is 3. Then we will use the zero product property. So don't be afraid because this has less information than the other one. You're still just going to set this equal to 0 and divide by 3. And if you divide 0 by 3, you'll still get 0. Don't be afraid of zeros on the top. They produce an answer of 0. And then x plus 3 will equal 0 here, giving you x is equal to negative 3. And those need to be written as x-intercepts. So 0, 0. And the other x-intercept is negative 3, 0. One thing that's really interesting about 0, 0 is watch what happens when I do the y-intercept. When I do the y-intercept and I find f of 0 and I plug 0 into the function, again the function is 3x squared, so I'm going to have 3, 0 squared plus 9 times 0. Everything cancels out. Don't let that freak you out. These are all equal to 0. So f of 0 is 0, and what that tells you is that your y-intercept is also 0, 0. This is really important on every problem for the rest of the time that you take Algebra 2 or Calculus or Pre-Calculus or even Trigonometry. If one of your x-intercepts is 0, 0, your y-intercept is guaranteed to be 0, 0. They have to be the same thing. So let's take a look at how that works when we graph it. We're going to start by graphing the vertex, and I forgot to tell you what 27/4 was. So if you take 27/4 and that's confusing to you, 27 divided by 4 is 6.75. So we'll use that when we actually graph it. Okay, so we're going to go to negative 3 and 6.75. So sorry, negative 3/2 and 6.75. It's actually negative. Forgive me there. I noticed that I put an addition sign there, and you got to just be careful, right? So that's a minus, so that should be a minus. We fix that here. And it's important that you see little boo-boos like that because they're going to happen, right? And you need to make sure that you see someone go back and check. All right, so now we're going to graph it. I just saw that out of the corner of my eye, and I'm glad I caught it. So negative 3/2, that's this part right here. The axis of symmetry is x equals negative 3/2. The vertex is negative 3/2, comma, negative 6.75. So that's about, we'll just go right about there. It's an estimate, doesn't have to be perfect. It's off the graph anyway. And then we're going to graph the x-intercepts. The x-intercepts are at 0, 0 and negative 3, 0. So we're going by ones, so 0, 0, and then 1, 2, 3. You can see that's perfectly in the middle. And the reason I don't have to graph the y-intercept is 0, 0 is actually on both the y and the x-axis. And so then you would graph it. And the reason that we're doing these variety of graphing is that one would be sort of hard to do from your transformational graphing, because how do you go 1, 1 from negative 6.75? It's important to understand these differences. And so that graphed it without having to worry about trying to move the transformational graph. It does have two X-intercepts, as we predicted, using the discriminant. All right, let's do one last problem. Okay, so this one right here has a fraction in the front, and I wanted to show you what that would mean. So the discriminant, okay, let's see what happens, is still going to be b squared minus 4ac. A is a fraction, b is negative 3, and c is positive 3, so we would have negative 3 squared minus 4 times a, which is a half. You can see why I picked a half. It's going to make the multiplication fairly simple. So here we would have negative 9 squared, which is 9. Remember, when you square something, it's always positive. This will be a subtraction because there's only one negative in this expression. And then we have 4 times a half, which is 2. 2 times 3 is 6. So we end up getting 3. Still going to have a real solution, right? We're going to have two real solutions here. And we're still going to have two X-intercepts. But this problem is not factorable, which is important to understand because that means we're going to have to solve it slightly differently, which we'll talk about when we get to that portion when we do X-intercepts. Okay? So let's talk about putting this in vertex form, okay? Because we're going to have to factor that out. It actually works really nicely. And you might say to yourself, why is he giving us a fraction there? Because I just want to show you how that works. It actually is not as big of a problem as it seems like when we first get started here. We're going to start the problem as we normally would by getting rid of C and putting it over here so that we have a blank to hold that space. Okay, and so then what we're going to do is we're going to factor out the lead coefficient, which in this case is 1/2. So how do you factor out a half? Well, to factor out the 1/2, you're going to divide, that's what factoring out does, you're going to divide negative 3 by 1/2, which would actually reciprocate and multiply and make it 6. So that works out pretty well for us because that's actually going to complete the square pretty nicely because half of 6 is 3, right? So over here when we take half of negative 6, we're going to get negative 3. And then when we square it, we get 9. So as I said, it's not as bad as it looks. You just have to know that when you divide by a fraction, you reciprocate. Don't forget to add the 9 over here and then multiply times 1/2. All right, so we're going to have to clean up this side as well. So 3/2, if I want to add it to 9/2, let's see what that looks like. So negative 3 plus 9/2. I'm going to have to multiply this thing by 2 over 2 to make it 6/2. Negative 6/2 is negative 3. And I'm going to add that to 9/2, which comes out to positive 3/2. Don't forget there was originally an f of x here. And it's positive, so we'll say plus. And this side over here, we have 1/2. And the factorization is always mirrored. It's just this, right? So don't ever freak out. So we're going to have x minus 3, x minus 3. And then over here, to do this part, we'll have 1/2 x minus 3 squared. And then we're going to move this piece back over to the other side. And this time I'll be a little more careful with making sure I keep the correct sign. It's important to see those little things that happen. Nobody does math perfectly. And the main thing we learn to do is to learn from our mistakes. All right. So let's take a look at what happens next. Okay, so that's the vertex form. So my vertex is going to be positive 3, opposite h, and then minus 3/2 as the k. And my axis of symmetry is going to be x equals 3. So now let's take a look at how to solve for the x-intercept. When things don't factor, they're actually easier to solve from this right here. Because remember, if you go back and look at the notes, to find an x-intercept, you can actually solve it by setting vertex or standard form equal to 0. In vertex form, you already have all the work done. It's already the completed square has already happened. So I'm actually going to do my x-intercept not using the standard form. I mean, I'd have to use the quadratic formula, but I've already done all the work. So why don't I use the completed square form, otherwise known as vertex form, to solve this problem? And don't worry, it's going to work out nicely with all those fractions. I set it up like that for you. So we're going to reverse the order of operations, starting with addition and subtraction. All right, so we're going to add that. So this will inverse out. And then we have 3/2, and I know you're afraid of those fractions, but they're going to cancel. Don't worry, as long as you do it in the correct order. So we did subtraction. That means we get to skip to multiplication. So don't ever distribute this. It doesn't have the same exponent. So we're going to multiply times 2 to cancel this. And then I'm going to multiply 2 over here. And as you can see, that wasn't so bad. So we end up getting 3, and that is equal to x minus 3 squared. And then we will take the square root. Don't forget your plus or minus here. All right. And so then we end up with plus or minus 3, square root of 3, and then you get x minus 3 here, and then you add 3 to both sides, and you'll get your x-intercepts, which to graph them, you're probably going to want to type them in a calculator because they are irrational. So your x-intercepts are 3 plus or minus the square root of 3 is equal to x, which written as x-intercepts. You can see I already typed them in here, but we'll write them out. The first one is 3 plus the square root of x, plus the square root of 3, 0, and then 3 minus the square root of 3, 0. And I typed them in so we could graph them in just a moment. The y-intercept is much easier, right? Because we're just going to plug 0 in, and always do that from the standard form if you have it, because you're going to get c. So here we would have 1/2 0 squared, and then we would have minus 3 times 0 plus 3. These cancel, and you honestly could have just written down from the beginning that f of 0 equaled 3, meaning we plugged in 0 and we got out 3. And you would get the same thing if you did it here, right? It would just be more work. If you plugged it in here, you'd have to add some fractions together and such, but so you always would do that from standard form. All right, let's get started graphing it. You can see that I already graphed the axis symmetry here at x equals 3, right? That's already done. And then we're going to graph the vertex. The vertex is going to show up at 3, negative 3/2, which is 1.5. So I'll put it right there. So 3, negative 1.5. My x-intercepts are these crazy irrational numbers. So they're approximately 1.2. So 1 and 0.2-ish. Oops, let me make that bigger. So 1 and maybe 0.2-ish right there. And then 4.73. So 1, 2, 3, 4, a little bit closer to 5. Notice how that line of symmetry helps you do that. The y-intercept is 0, 3, which is very helpful because if you needed to, you could also kind of graph another one right there because it's symmetric. And then don't forget to actually draw the parabola. So one of the things I want to show you also that could easily happen is your teacher could change this equal sign, right? They could change this equal sign to a less than sign. And what that would mean is it would mean graph below the graph. So we would be shading all of the region that's below this. And sometimes it helps to draw a little person on here, right? And you can see below means feet. So you would actually shade all of this when somebody says less than the parabola. And notice that this one also, just to kind of correlate some things back from Unit 1, it doesn't have the equal sign. So that would mean you would actually have to go back and then make it a dotted line. And you might remember that from previous units or from even Algebra 1. So I just changed it subtly there at the end so you could see what would happen if we had a less than sign as opposed to an equal to sign. And why don't we go back and change another one? So let's take a look at the first one. It's a little bit easier to understand than that one. So let's say I made this one a greater than or equal to sign. What that's going to mean is it's going to be a solid line. We're not going to change that. But when we graph the greater to, again, it helps to draw a little person. So it seems to be very helpful. Less than would be below the feet, but greater than would be where the person's head is, and you would just shade right here. And that would be what it would look like if it were greater than or equal to, because I didn't have to make it dotted. A lot of information there. You might have to rewatch parts of it. It's a great review for the entire chapter, so I would go ahead and take a nice look at that, maybe watch parts of it twice. Thank you, and I hope you enjoyed this video.